Hello, thank you for the introduction, Edmund. So I wonder, do you see the presentation clearly?
I saw it earlier a little bit clearer. Right now it's pixeled, so I'm not sure whether that's the case for others too.
You probably have some windows in front of the presentation.
Could be.
They probably get blocked from the WebEx.
Yeah, it was before, but now they should be removed. Let me close everything.
Now we see the presentation, yes.
Okay. So let's go to the agenda. Do you all hear me?
Yep.
Yeah, thank you. Just making sure that it happened some earlier time that I was talking to the void. So the agenda, first point would be a quick VTune overview. These are more marketing related slides, or for those people who don't know VTune, give a course overview of the capabilities of VTune. Then I would like to introduce the command lines playbook. So I wonder if it's also in the where the PDFs are now. This is a text file that has some steps in doing some hands-on. So maybe when my presentation becomes boring, you can then entertain yourself with the doing the hands-on training in parallel. And so when you already have the DevCloud account, so it was probably said yesterday that everybody is welcome to create an account there on the DevCloud, and it's the easiest way of trying tools and compilers and so forth. Then we would like to motivate that the start of a profiling session, especially with an unknown application, would be to use the application performance snapshot APS. So APS is now more tightly integrated into VTune, but it also has a script in the VTune bin file, a bin directory to do independent of VTune the APS profiling. Then a short overview on HPC analysis, because I think for the people listening here, HPC analysis is crucial. This is some kind of orthogonal to the GPU analysis, but it contains some interesting analysis types, especially for OpenMP analysis, which I like. Not the OpenMP, but the analysis. But then we turn to the GPU analysis, showing example slides from GROMACS. It's not too interesting, probably because the hardware we need to use, the hardware that is already the hardware that is released already, and therefore the best option is to use the DG1 or the Iris Max GPUs that are available on DevCloud. But these analysis types get more interesting when you turn to the ATS performance nodes that are also available under NDA on the DevCloud. So some might have, or from some compute centers working closely with Intel, get an NDA admission to DevCloud to use the more advanced GPUs, and later on we will also have first samples of PVC running in the DevCloud. There are already 2 nodes, but they are only for more or less internal usage. So the last point in your script, there is still summary, but going through the slides, I saw that there was no summary at the end. So the last point is documentation. So let's go to the next slide. And this is an overview on the capabilities of vTune. And so you see, following the one API philosophy, we are targeting for all kinds of compute devices like CPU, GPU, FPGAs. We are targeting to threading, memory, cache storage, offloading, and even power analysis. You might need some special drivers from some special analysis types, but normally when you have installed the perf drivers, you can use just the perf drivers on your cluster instead of the internal vTune drivers that can be also installed. But we often see that compute centers are quite reluctant to install this because this has to be done per node, and this is some overhead for them, so it's better for them to use the perf drivers. Well, you see on the right side that there's on the right top, let me do this. Right top, there is a tree diagram, and you usually start with performance snapshot as a first step. And when you did this analysis inside vTune, then it will highlight all the other interesting analysis types as an outcome of the performance snapshot analysis. So this is quite nice, even though sometimes it's a little bit misleading. For example, we have a code, sample code that's just running GPU and using the CPU only to launch kernels. And then vTune wants to convince me that I have to improve the CPU performance for this code. So, well, you know best what to do next, but it makes some suggestions what kind of analysis would be the next. And below this, you see here is some picture of how it looks like in vTune source analysis on a GPU, and you get even the mix of GPU instructions shown here per source line. And when you click on assembly, unfortunately, with my samples I did on this probably outdated drivers on the dev cloud, the assembly was not shown, but normally the assembly is shown, and you click on the source line and see the assembly code that's associated with the source line. That's very nice. Sometimes for GPU optimization, it's good to know something about the GPU assembly. And below that, you see here the memory hierarchy diagram that comes also with the GPU analysis, and you see all kinds of the different components here. Like here is the GPU, and you see the execution units, and you see how many are active. And we want to, of course, maximize the active and minimize the stalled and idle time on the GPU. Then you see that we have a connection here to the L3 cache, and you see the numbers in gigabytes per second for the communication with the different caches. And here is the GTI, is the graphics transport interface. I think it's the correct name. And that's between the L3 cache and the caches on the CPU. And so this is more or less the PCI here performance that you see here. So not spoiling too much with the GPU performance analysis, but going to more overview. So this is, can you say, some kind of a marketing slide, but it gives an overview what kind of analysis types are here and for which situations they are made. So starting from single thread, multi-thread, system analysis, and then the media OpenCL applications that would be also, I would say now the GPU compute is also under it. And then we have an HPC and cloud analysis. So lately there was an issue people tried with using vTune under Docker or in a Docker container, or you can use it from a compute node where the Docker container runs and analyze the whole node, and then you can filter out the Docker activity. So that's also working. And then we have special memory and storage analysis types, and we have a rich set of filtering and analyzing further the data to have the right views for your special experiments. And it fits into your environment, so you can, when you have Windows, it asks you to integrate this into Visual Studio, or it can also be integrated in Eclipse, I'm sure. So this is a quite old slide here showing the bottom up. So bottom up is most times the most interesting analysis types for HPC or hotspot analysis. And you see here functions listed on the left side, and you see results of the analysis for this function. So you can see here the utilization. So this is configurable sometimes. So it's counting, yeah, let's say it's most times it looks very bad because it's counting all the hyperthreads also, and wants ideal scaling over the hyperthreads, which is never achievable. But if you are unsatisfied with the analysis here, you can change the criteria. Then you see for OpenMP, you could see the spinning time can be analyzed, and then other sources of overhead like scheduling, reductions, atomics, and so forth. And on the bottom, you see here are the different threads. So you see here the OpenMP master thread and the other threads, and the brown stuff is usually the good stuff here. The red is the bad, and the green is where it's running, but not doing anything, so not consuming any cycles. So this is the overview on vTune, and maybe many people of you already know this. Sorry for telling you again. And for this section, I had prepared a playbook. So the playbook is, yeah, well, you can put this into a PDF as well. That looks nicer. But when you have tried to copy things out of PDFs, you sometimes get issues. And on a Linux cluster, you must find the right PDF viewer and so forth. So it's less overhead to have it in a plain ASCII file. And I prepared this ASCII file. It's probably already in where the PDFs are found, but if not, you can also have this on the dev cloud in this shared directory here shown here. So there's one shared directory. I hope I have given you all the permissions, and you can copy the playbook. There's also the playbook for the inspector as well. So coming to the next point. And an important question is always how to start an analysis. So what would be the first step if you don't know for sure that some kind of VTune analysis fits best for you, like the GPU hotspot analysis or whatever? But if you just want to have to do an performance validation and you are looking for the best analysis types in VTune to get the best performance. So VTune offers all these analysis types with additional knobs, and you can fine-tune your analysis very much, but sometimes people get lost. So our experience was in earlier times that many people started with the general exploration analysis type, which is the most involved and the hardest to understand because it's testing all the micro-architectural counters. And so it's probably best to have some kind of meta tool or starting tool that provides you some guidance in what to do next. And this tool, for this purpose, the so-called application performance snapshot, APS, was invented. And APS does the first analysis over the whole application and gives a summary output in how your application does and which kind of features of your application are not running sufficiently, and so you should have a look on it with another VTune analysis, or even use another tool for example, when you have an MPI analysis, you might consider using iTech for more insight. And the APS analysis has normally, where's my pointer here? The APS analysis has some, here it is, has some options, so you can decide if you want to concentrate more on the hardware counters for memory and other stuff, or if you want to concentrate on OpenMP and MPI, and then you can switch off the hardware counters and just concentrate on the MPI or on MPI and OpenMP. APS can be used also, can be of course used plainly for MPI and OpenMP, and is very high scaling. So you can even for jobs where iTech is not working properly because the trace files gets too large, then you can use APS up to 10,000 of ranks. So my colleague Dimitri will tell you more about this in the second last presentation about MPI. So the usage model is quite easy. You have a help system. This is quite handy to have all the tools have a help flag and an extensive help menu, and so you can learn about APS just by using the command line help and getting all the features you need. And when you run with APS, you can why is this always the maybe I shouldn't use the annotations. It's working properly. You can run APS by just writing APS in front of your application, and and the application parameters, just as a script in front of the application. And you can do the same with MPI, and then you exchange your normal application executable in the MPI run with APS and use the application itself as parameter. And then it will write out for an analysis for each rank, and it can also will summarize the analysis in a summary file. Sorry, I have some issues here. Okay. No, it's gone. Sorry. So that would be the APS output for the application I was using in as the hands-on in the playbook. So this is an N-body program that is simulating gravitational forces in a very simple way, but it runs very nicely, and you see you have from the 17.36 seconds CPU time, 16.93 seconds are on the GPU, and the GPU utilization is 95.3%. So that's very nice. So there's no need to optimize here from this perspective. But VTune wants to motivate us to increase the physical core utilization, which is nonsense here because we just want to have a simple program running on the GPU. But for other applications, like for example GROMACS, when running GROMACS in a hybrid mode with one part running on the GPU and one part running on the CPU, you may use this to may increase the physical core utilization, for example, for this PME branch that André was talking this morning about. Well, you see, also we have some memory analysis, but this is all for the CPU analysis, which is not interesting here for this code. So APS runs with MPI and OpenMP analysis. The hardware drivers can be switched off to avoid overhead, and it shows you the max time consuming MPI functions. And as I said before, Dimitri will show you more about this later. And what's interesting is the measurement of the imbalance time, which is basically waiting in barriers for OpenMP and MPI, and also waiting time in collective operations or in receive operations, or when the send is not there. So it's computing all the wait time, which indicates that your application might not be perfectly balanced, and you can gain the time that's calculated here if you have a perfect balanced application. So the HPC analysis is interesting probably for many of you, and it gives you a detailed OpenMP analysis, for example, which I like very much. And it gives you memory and bandwidth analysis and NUMA analysis, for example, to see if everything is properly, for example, an OpenMP application, if all the threads are properly pinned, and so there is no NUMA traffic that one thread wants memory from another socket and then has some inter-socket memory traffic. Some MPI analysis, but better use ITEC for this purpose to get more in-depth overview of MPI behavior. So the command lines for OpenMP and HPC, you see VTune collect HPC performance is the Analysis of choice. Okay, ITEC, sorry for not spelling the acronym. So it's the trace collector and analyzer, and it's say same people that developed on VTune library, tracing library, sorry, on the vampire tracing library, were then doing ITEC for Intel, the same team from Pallas company in Germany where I also worked before Intel. And this is the preferred MPI analysis tool. Threading analysis, there's a special threading stuff here, and threading analysis that you can use. And there's, of course, a rich help menu, which is very handy. So this some one colleague has already complained about this. I've taken older slides here for the OpenMP analysis, and well, you see this is very nice because you really get inside the parallel regions and can even on finer granularity, not only parallel regions, you can have an analysis and you always get a potential gain. How the potential gain is calculated, I will tell you later, or there's a slide. And well, this is, you see the test application is a conjugate gradient from this, I think this was called the Berkeley benchmarking suite, which is quite old, and but people like to use it as some proxies for HPC codes. And you will see the next slide. Here you see that I was using an older version, or not I, but who has generated this slide. I was using still the VTune amplifier, but the analysis should look more or less the same for the actual VTune as well. But I like this slide because it explains how the ideal time is done. So you have a parallel region, and you see in the parallel region the effective time here in green. Then you see different states like the forking, the beginning, and you see yellow here is scheduling, and red is for lock spinning, for example. And in the end, the white stuff is just the imbalance, just waiting. When some thread is finishing earlier, it has to wait in the barrier until the last thread is ready. This to get the ideal time, you take all the effective green time, sum it up, and build the average. The average is then the ideal time, and then the sum of all the average per thread on each per thread for each source of ineffectivity is then the potential gain. And most of the time, it will be just the imbalance, just the waiting time in the barrier. And you see on the picture below, it's shown here that we have left the imbalance, and you can easily guess that the pink fields are the ones that you should have a look on, and it tells you that there is a huge imbalance here for this special OpenMP region. And there is just a tiny little bit of scheduling, but you can forget about, so it's all imbalance. And then you can can try to avoid the imbalance for dynamic scheduling, but that's sometimes you switch on dynamic scheduling and then the imbalance goes directly into the scheduling overhead, and then you have to balance on how to run this application best. So here's just another view that shows that not even parallel region are timed, but also when you have barriers inside the parallel region, either implicit ones by, for example, using OpenMP. Okay, there seems to be something missing here, but I thought that that you download the so in the chat there's somebody complaining about the .hpp file is missing, but I thought that you download the clone, the sample directory, and then just copy the CPP file into the right location, because you need also other files, other stuff for compiling it. Well, you see, you have a parallel region, and even when there are barriers inside the parallel region, it will with more fine grain show each barrier section inside the parallel region. This is quite nice for OpenMP analysis. But let's proceed. So there are also additional analysis for memory and bandwidth, which are very nice. So with memory, you can really see how much impact some arrays might have. So you see arrays, see a list then for memory allocation locations, and how this memory allocated there is influencing the whole performance. So there is some MPI performance analysis also possible. Please check the cookbooks. So the link to the cookbooks is at the end of the presentation. This is more CPU than GPU related. So today we are talking more about GPUs, and now just one slide about vTune and MPI. Usually people ask when they hear the vTune talk, what about MPI? How shall I, when I have MPI on a cluster, how shall I use vTune with MPI? And so there is one switch, the -gtool switch, which is quite handy. And the link on the bottom of this page will show you some experiments done using the gtool flag. But I like even more the IMPI gtool environment variable, which has the same effect, but it's more handy because you can keep your scripts as they are, but just set additional the IMPI gtool environment variable. One example is printed below, and you can use IMPI gtool and use your vTune line together with colon, and then 0 would mean that vTune is only executed on rank number 0. You can put a list of ranks here, or you can put colon all for all ranks. But I wouldn't recommend this because this is generating too much overhead. While also when you use vTune on a single rank, this rank can get somehow slower and introduce a load imbalance, so that could spoil the experiments as well. Just some thoughts. So GROMACS on DevCloud. So the hardware we can show here, or the results for the hardware, is a little bit outdated or not as powerful as what we have on the NDA section. The non-disclosure section of the dev cloud contains more powerful GPUs, and well, some probably of you already have admission to this. But for testing it and testing the tools, it might be also good to use the existing GPUs on our cluster, on our dev cloud. So what does the vTune GPU analysis do? So it times or shows the host API and the GPU kernels, and it has a detailed source view on kernels. So it tries to get the timing per source line, but this is even more complicated, I guess, than doing this for CPUs. So it's basically a basic block analysis. So basic blocks are timed inside the kernel, and then by some heuristics, it's more or less guessed how many, what fraction of the time of a basic block is due to a certain source line. So it's not totally crisp here, but as in quantum mechanics, the more you want to know, the more blurred the results become and more disturbed. So that's a compromise, but working quite well. And we have a lot of bandwidth data here, which we can show with the hierarchical memory diagram. And yeah, I will show later. And estimates for timing per source line with basic block timing. Also, there is an estimate for the memory latency. So you see, instead of timing per source line, you see latencies shown, and the some guess of the performance for the source line. So that is a SYCL version of GROMACS. So Andre hasn't shown this in detail. So you can also get all the information from the documentation of GROMACS, but I've done this here for people who are interested. So just clone the master branch. There will be a release branch now very soon, the 2022 release branch, which also contains SYCL code. And but normally the master branch is quite stable, and you can clone it. And then there is a workload that comes from the Max Planck Institute in Göttingen. So actually the scientist who is providing it was the first who I was talking about over GROMACS. And there is some hints here for using CMake to build it. So you see the crucial flag is here the dgmx_GPU equals SYCL. And then you can point the FFT library to MKL, then the PME call will be done with MKL. And the run is copied this from my execution script. So Exadir is the, as you can guess, the bin directory. And then you have some flags for the internal MPI. Yeah, thank you for providing the information about this in the chat. So, but normally my idea was to copy the spoiled source file into this and then compile as usual. You can set the number of OpenMP threads, and minus NB is for the non-bounded forces, which are 90% normally of the code and which have been ported to SYCL. And you can say if you want a CPU or GPU mode. And the PME is here still with CPU mode. So this is brand new. So we are expecting very soon a GPU branch for the PME. And then comes the input file and the number of steps that you want to take. There are some more stuff that you can add, but I don't want to overload this too much. This would be the application performance snapshot for GROMACS. And you see on the right top side, you see the overall summary, and you see a lot of summary serial time. But this is, sorry for that, is an artifact that it's just running a few cycles at the beginning. So this is all the initialization time, and without this, there wouldn't be much serial time left. So there would be very good OpenMP scaling, and OpenMP imbalance here is shown about 1%, and some memory stalls. Vectorization is good too, and will be probably also better when you run more cycles, or you can even add some AP calls to the application to filter out the regions of interest. And then there is the GPU utilization, which will be also better when you run more cycles. Yeah, and you get here the GPU utilization, but also the vectorization should be very good, because this is all mapped to intrinsics. All the stuff when you use instead of the GPU, the CPU, then everything is mapped to intrinsics, and you get very good vectorization timing. Well, so this doesn't tell us very much here. So we go on and go to the command lines for the GPU analysis. So the analysis type would be the GPU hotspots here that's used, and you can either add your own directory for the results, which might be handy when you have some kind of scripts and want to copy then the contents of the scripts to something else, and then the executable and the args. And the next level would be to have a full instrumentation. So there are some levels in between, but I don't want to take every step. So this is the instruction count. This is a very involved analysis, because it has a huge overhead. So when you do this, you can expect that the application is running only quarter of the speed and less or something. Okay. Okay, there seemed to be, somebody's writing in the chat privately to me, seem to be still mistakes in the playbook. So hopefully, like playbook line number 126 is not correct, and the correct path, yeah, well, can talk about it later. So let's proceed here. No, I'm getting into the same trouble again as before. Somehow it's losing my pointer. We have the source instrumentation here as the next step. with the timing of the basic blocks. This is quite nice. So you see timings per line, but don't trust it completely because you know it is some guessing in it. So it's using basic blocks and guesses inside the basic block what's the time fraction per line. And so it's not totally crisp. And the last one is the instrumentation with memory timed, and so you get memory latency timings as well. So this is we can now start with the demo, and I would like to go on switching now the presentation to so I stop sharing and now sharing. So that's the one we have done differently in the past. So this is, oh, sorry, I've made a mistake. So normally we were recommending when doing vtune using the command lines on the cluster and then packing all the results into one directory, tar it and take it to your own machine and run it on a local vtune. But this is quite unhandy because you need more or less the same version on your laptop and on the cluster for vtune, and you have to transfer the data all the time. But now, as described in the playbook, it's possible to run still too many. Okay, do you see? Yeah, you should see now the vtune. And in the playbook, it's described that I'm doing allocating a node on the dev cloud, a compute node. And in the next step, I'm establishing a tunnel from my laptop to the dev cloud and extend the tunnel to the compute node. Then I can start, as described in the playbook. Then I can start a vtune server, and it will give me a line here, and the line is or give me an HTTP address, which is here just the local HTTP. And I wonder if annotation works here. The local HTTP address, and I can put it in my browser. And probably there's also a certificate when you do this at the first time. So it's storing it. So I cannot remember what the first time I think there was a certificate that you always also have to use, and then you have to start pipe this in the browser. And pipe this in the browser, and then you will ask to probably for another password, a passphrase that you have to give, and then it magically opens VTune on your compute node, and you can directly use it for defining projects, or you can also use the command line and put the results of the command line locally on the dev cloud in the special folder that I used by VTune, or you can start the VTune server by also adding a source directory for the VTune results. But here I just started it, and I can have a session, start a new project here, and let's call it EuroCC. And the next step is that we need the exact location, and I have too many files open. Just pipe it here for the N-body application, which I built before. Well, first we can try it without the application parameters, but I learned, in addition to what is in my playbook, there is the possibility of giving runtime arguments. So you can, the first argument would be the number of particles, and the second one would be the number of steps. So in the playbook I've written, you can change the source code, but there's also a parameter to this application. So then we have to decide which kind of experiment we are doing. Maybe because this is quite quick, we can do a performance snapshot. Okay, and then we go here on the bottom on start. And because I have changed the parameters a bit, it will take a bit longer, so 17 seconds, I think. It will compute and give more or less the same that we have from our experiment with the standalone APS. So here the date you see on the bottom, the normal output, and it's quite good performing for this hardware. So you can see it was written something like 1.1 gigaflop, teraflop, and was this teraflop? Yes. Which is quite good. And then it gives you here in the tree the next analysis types we can use. But we see here the stuff we've seen before, and a very good active time for the GPU activity. And so we can choose here for the GPU media hotspots. And by the way, on the bottom you see the platform information. And then you can see here the processor name is Cascade Lake. So probably a little bit outdated already. And the GPU is a Iris Xe Max Graphics, the DG1, which was the first discrete graphics from Intel. And you see 96 EUs, which is much better than the 24 that you get normally from the integrated graphics, but much less, of course, compared to the new GPUs that we expect later this year. Okay, what do next? Next, we want to do GPU media hotspots analysis. Now we can keep everything as it is, but we have now the chance here to change the characterization mode. And first is the overview with not too much overhead, and then we got the dynamic instruction count. But you can also ask for source analysis and then have some instrumentation up to the source line, and you see that there is more overhead here expected than before. So yeah, what shall we do now? I think I stick with the most easy one. This will run again for hopefully not too much more than 17 seconds. And will show us an overview of the GPU performance. So the overhead is quite good. So with the instruction mode, there would be far more overhead. So it would be probably running 3 times as long. And then you get some information. Here's some bandwidth information, but this looks all very bad. This is the communication with the over PCI, but you can also go to the internal mem. Doesn't look much better, but at least the internal GPU L3 bandwidth is quite nice here, going up to, what is it, 168 gigabytes per second. So not boring you with this. This is memory hierarchy diagram, and you can see the different steps of or different features here of the CPU plus GPU system. So the CPU at the bottom, and the CPU exchanges data with the last level cache. The last level cache goes into the PCI, and then through a traffic router to through the GTI, which is the interface on the device to the PCI, and then into the L3 cache. And then you see the memory here, 164.3 gigabytes between L3 and the actual execution units on the GPU. And the other, on the bottom, you can see the different kernels, and it also shows the work size and the local work size. And for more complicated application, it will show also the subgroup sizes. So the platform diagram shows now how it is running. And you see here, like in OpenMP analysis, you can see the kernel execution time, and you can see some information about each kernel, how long it's running, what the local size is, and what the SIMD width is. SIMD width is, Andre was talking about this morning. So for GROMACS, SIMD width 32 was imposing too much register spills, and for our GPUs up to the ATS GPU, which is in the NDA part of the DevCloud, and they have to use SIMD with 8 here for the kernel. But later on for PVC, we will prefer SIMD with 32 also with GROMACS. And you see here the kernel timing, and on the bottom, this is hard to read. This is some synchronization event on the host. And normally for Gromax, for example, we try, or Andre tries to overlap the kernel time with CPU time or useful CPU time. And you see much less of this synchronization that the host needs for ending the kernel. So there's then overlap of CPU and GPU time. And here you see one diagram that shows you how many execution units are active. So this is running wonderful. All green means all execution units are busy. And there's just a little bit red stuff, which is then which is indicating idle or stalling time. And then you can see how many computing threads are dispatched. What is the memory access here and the memory to the L3 bandwidth. And on the left side, you see the maximum values that are also measured internally. So this is all probably a little bit boring. So maybe we go to the more involved VTune analysis for Gromax. And I prepared some experiments here, and we can just switch here to the Gromax experiments. And well, this is also not a very nice value here for the elapsed time. So 43% of elapsed time are stalled or idle, but this is well, due to the hardware here and to the fact that I'm just measuring the first iterations. So if a more clean analysis would just cut out the first iterations and just time where everything is in lockstep, because with Gromax you have it running for sometimes for days, and so the first few seconds are not so interesting here, and you can cut it out. So what happens next? Let's go into the graphics and the same diagram here. Then you see some more information about what are the timings, and these timings are per kernel. So you can read the numbers here also in the grid below. So the 1.6 gigabytes read of GTE, these GPU memory bandwidth on the bottom, the read time, the 1.595 gigabytes per second, and in the other direction is the write, 327.9 megabytes to the PCI. And when we change this, for example, to this ZE command list append memory, which is the host API, the level 0 API for memory communication. And you see that these numbers change, and we have a lot more. Should be. Yeah, more data transferred than before. And we see that this is 99.4% idle, which is not so important, I think, because it's just working before and after kernel to communicate data. So that would be the overview, and then let's go to the memory instructions. So I told you that there was another way of viewing the data. where the instruction count is, the instruction types are measured. And you see that the timing here goes up. I haven't got in mind what was the previous timing, but it should be much factors higher. And you see practically the same kernel here. So it's always from source more or less the same kernel that's counted here, but sometimes called with different sizes. And so this can be also looked together, but it also can be differentiated in the different kernel invocations. So let's go to the graphics again, like before. This diagram looks a little bit more interesting now. And you see here the main kernel. And we have here this grouping function. And this is source computing task where just the one source kernel is shown. And when we go to computing task, we see the different invocations. And then you see information about the work size and the global work size and the local work size. And the local work size to some extent determines the SIMD-ness of the kernel. So here for this setting of the local work size, we get SIMD8. And for the work size will change then when we go to PVC, and it will be more like the settings we have or they are using for the CUDA version. And so then this will result in using SIMD32 here for PVC later on. And you see on the right side that the mix of instructions is shown here and the SIMD utilization. So you get some information about how efficient your code is running and what kind of instruction it is using. But that would be still quite boring. So it's probably more interesting when we go to when we go into the source view. And then you have looks a bit strange here that it starts with the return statement, the kernel. We have the instructions for the whole kernel, and then we get these estimates for kernel timing. And wonder if you see my mouse. We see here the constant float3 value, and yeah, the float3 Andre was talking about is in SYCL. The float3 is using internally more or less a float4 in SYCL and OpenCL, and so KTH has written a class that's doing a float3 with just 3 values and not 4 values. But this has shown sometimes to be, or a colleague has identified that this was a little bit inefficient here. But that would be one point to where will be working in the future to optimize. Or Katie or Andre will be working on it. And when we go down, we should see some more action here. And you can see the mix of instructions, and this is quite nice to understand. So the red color stands for control flow, and you see, oh, well, this is an if statement, and this is of course then causing a lot of instructions for the control flow. And so you can view your application here under the aspect of instruction mix. Then we switch in the end to the source view. Okay, that was the source view experiment. And you can go into this. We have done this for the other application as well, and see the individual kernels. Let's do this. Zoom in and filter by selection. And you see then the individual kernels here running. And you can see this is here, the big one is the non-bonded, and there will be in the beginning some preparation kernels for exchanging the memory or sending the memory from the host. And then you see here the host API calls. And currently my colleagues are working on improving this this low-level runtime stuff, because for GROMACS you need very low latency, so the kernel timings are quite short in contrast to other applications, and you need very low latencies to get good performance. And so my colleagues are working on improving the runtime for SYCL. Then we can also double click on the kernel name and got the source view. I'm sorry that this didn't work here. I don't know why. Normally you can click here on assembly and then get also the assembly view and click on a source line and see the assembly with the source line. It's probably because this stack for the, where's the interesting stuff? Oops, something went wrong. Maybe I have to reset this, because then it has not enough data. Let's see if this is better. Yes. Ooh, sorry. So then we can go and find the places we saw before. So for example, this was one place where a lot of instructions were shown. And we also see here a lot of instructions. And so we have, it's not totally crisp, so it can be that probably there is some blurring in some source lines not getting really this timing, but at least you get an indication where something is happening and where you have to look deeper at and change something and then take a new trace and see if things have changed. So this is probably quite nice to have. And oh wow, here's a better one. So that should be investigated further probably. But we have to first look how it looks on a better hardware, because it makes no sense to optimize here for this DG1. And in the end, it's running quite well. So it's a quite cost-effective solution to use for students, for example, this with DG1. And later on, I think in this year, we will have the DG2. This will provide even more performance. So basically I'm done here. So don't want to. Are there any further questions? So I probably don't have to switch to the presentation back for the ending slides. So there was a slide about documentation, and please have a look at it. And well, I wonder if all issues with the playbook are now sorted out.